You know, we trust our own eyes to drive every single day, but how can we ever really trust a machine's? That's the billion-dollar question at the heart of self-driving cars. So today, we're going to dig into exactly how engineers prove, beyond a reasonable doubt, that a car's perception system is actually safe enough for our roads. Let's jump in. All right, here's our roadmap. First, we're going to have to redefine what safety even means in this new world. Then, we'll climb what I call the five-step safety ladder, which is how engineers build confidence from the ground up. After that, we'll explore the wild world of virtual simulation, and finally, we'll see how it all comes together to hopefully build a safer future for everyone. Okay, so first things first, we need to start with a totally different way of thinking about safety. See, for autonomous cars, the real challenge isn't just about a part breaking down. No, it's about figuring out the limits of a system that's working perfectly, exactly as it was designed to. I mean, just think about it for a second. The world out there is messy, it's unpredictable, it's infinitely complex. A car's sensors and its algorithms have to make sense of all that chaos in a split second. So the real question is, how can we ever be sure we can trust its eyes? Well, the answer starts with this mouthful of a term from the ISO 21448 standard, SOTIF. It stands for Safety of the Intended Functionality. All that really means is making sure the car is safe even when nothing is broken. It's all about the built-in limitations of the technology itself. And this is where it gets really interesting. Old school car safety, what's called ISO 26262, that's all about what if the brakes fail. It's about hardware braking. But SOTIF asks a much harder, much more philosophical question. What if every single part of the system is working perfectly, but it's still unsafe? Think about a camera getting completely blinded by sun glare. Nothing's broken, but the car is now effectively blind. That is the SOTIF challenge. So how on earth do engineers even begin to tackle a problem that complex? Well, they use this really structured framework, which I like to think of as a five-step safety ladder. The whole idea is to build confidence from the ground up, moving from the simplest possible test to the most complex, one rung at a time. And these are the 5 rungs on our ladder. You start small, in the lab, testing the hardware on a bench. Then you check the algorithm's performance using data. After that, you put it all into an actual vehicle, you stress test it on a closed track, and only then do you finally validate it on the open road. See? Each step logically builds on the one before it. And this quote right here, it nails the entire goal of this process. It's not about trying to achieve zero risk. I mean, that's impossible in the real world. The point is to build a logical, evidence-based case to prove that whatever tiny bit of risk is left over, the residual risk, is at a level that we, as a society, can find acceptable. All right, let's start climbing. We're going to take a closer look at each of these 5 steps, starting in the most controlled, most sterile environment you can imagine, the lab. Step 1 is called bench verification. This is where every single piece of hardware, every camera, every radar, every sensor gets put through its paces long before it ever gets close to an actual car. The whole goal here is just to check the basic hardware. We're asking really fundamental questions like, is this camera lens focused properly? Is the radar's sensitivity within the specs? You're basically trying to catch any manufacturing defects or physical flaws right at the start, because trust me, it saves a world of hurt later on. Okay, up to the next rung. Now that we're confident in the hardware, the physical eyes, we have to turn our attention to the brain of the operation, the software algorithm. This is where the AI really gets put to the test. Engineers basically throw massive libraries of road data at the algorithm, either real footage or simulated. They're looking for 2 things. First, does it perform well statistically? And second, and this is a big one, did our latest software update accidentally make something worse? This is also where they hunt for weaknesses in what they call long-tail scenarios. You know, those super rare, bizarre events that you just don't see every day. So the hardware's good, the software's been tested. The next logical step, right? You got to bring them together and install the whole system onto an actual car for the very first time. And, you know, this is often where reality bites back. A sensor that worked perfectly on the lab bench might suddenly act up because of something as simple as glare from the windshield, or vibrations from the engine, or even the type of paint on the bumper. This step is all about hunting for those sneaky, unexpected problems that only pop up once everything is put together in its real home. Okay, so the system is fully integrated into the car. Now it's time to get out of the garage and onto a safe, controlled environment, the test track.
A test track is amazing because it lets engineers safely and, more importantly, repeatedly test for known dangerous situations, what the standard calls triggering conditions. Think about a pedestrian dummy suddenly darting out from behind a parked car. You could never test that safely on a public road, but on a closed track, you can run that exact scenario hundreds of times to make sure the system's response is rock solid.
And here we are. We finally reached the top of the physical testing ladder. The very last step is to take the car out into the wild, unpredictable chaos of the real world. Now, open road testing isn't really about scripted tests anymore. It's about discovery. The goal here is to find the unknown, unsafe scenarios, the things the designers never even thought of. This could be anything from a truck kicking up just enough snow to blind a sensor for a second, to the crazy light change when you blast out of a tunnel. It's about finding the things you didn't know you didn't know. So, we've climbed all 5 steps of the physical ladder. You'd think we'd be done, right? But here's the catch. Even with all of that real-world driving, there's a fundamental problem. You simply can't drive enough miles to prove the system is safe. And that's where the virtual world becomes absolutely essential. To put this in perspective, to statistically prove that a self-driving system is safe enough, you would need to drive it for millions, maybe even billions of kilometers. Trying to do that with a fleet of real cars is just, well, it's pretty much impossible. It would take too much time, and it would cost way too much money. So if driving it all is off the table, how do you test it all? Well, the answer is simulation. You create a virtual proving ground. That way, you can run millions of kilometers of tests in a fraction of the time, and you can explore endless variations of dangerous scenarios that you could never, ever stage in real life. But of course, for a simulation to be any good, the virtual sensors have to behave just like the real ones, flaws and all. And there are 2 main ways to do this. On one side, you have parametric models. They're fast and they don't need a ton of data, but that's because they make a big assumption about how the sensor works. And if that assumption is wrong, your whole simulation is inaccurate. On the other side, you have non-parametric models. They are completely data-driven and super flexible. They can be incredibly accurate, but they need huge amounts of data and can be a lot slower to run. It's a classic engineering trade-off, speed versus fidelity. So when you combine this really rigorous physical testing with the sheer scale of virtual testing, you start to see how this incredible ongoing cycle of improvement is created. Let's wrap up by looking at how it all comes together. So what are the big things to take away from all this? First, safety isn't a simple pass/fail test. It is a continuous, never-ending process. Second, that process always moves logically, from the simple, controlled lab out to the chaotic, real world. Third, simulation isn't just a nice-to-have. It is absolutely essential to cover all the bases. And finally, and this is probably the most important point, it's all a continuous feedback loop. When you find a new, unknown danger on the open road, that data gets fed right back into the simulation and the algorithm tests, making the whole system smarter and safer over time. And that really leaves us with one last big question to think about. We've built this incredibly detailed, rigorous process for the AI systems we have today. But as those AI systems get exponentially more powerful and more complex, will our methods for proving they're safe actually be able to keep up? It's something to think about. Thanks for watching.